Hello, in this video I'd like to talk a bit about calculus. In particular I want to think about differentiation from first principles. I originally taught myself calculus much earlier, before it was required in my given syllabus, and for some reason I've always had a real interest in calculus. It's certainly one of my favourite subjects. I think when you're a kid and you first learn of calculus, you hear the word calculus or you see it scrawled on a blackboard or something. It looks quite mystical and mysterious and what have you, but it's really not. It's actually quite simple when you understand it and you understand the logic from first principles. And so in this video I just want to talk about I suppose how I taught myself calculus, and in particular, for the sake of this video, how I taught myself differentiation, and also just work through understanding differentiation from first principles. And I suppose one needs to understand firstly, and I'm not going to spend a lot of time on this point, that the gradient of a line. Say you have the function. Say you have y equals f of x, which equals some straight line, say x plus 2, just something really simple. And we have our coordinate axes here, and we know x plus 2 is going to cross at 2 like this, and we've got a straight line that's going to look something like this, right? Well, we know to find the slope of a straight line. It's very, very simple, and you can deepen the thought for if this is x and this is f of x. Say x is 1. I'm just going to spend a few moments here, because one should already understand this really. So we say when x is 1, f of x is 3, so y is 3, and then that's 4, and that's 5, and that's 6, right? And right, because we're just plugging in our x values here. And notice, of course, that it's increasing by 1 each time. Y is increasing as x increases. Y increases by 1 each time, right? So you would have the point when x is 1, y is 3, so you could have a point there. And when x is, I don't know, say 4, right, that's 1, let's just say this is 4, and we can say, okay, y is going to be 6, right? And to find the slope of this line, which will be the same at any point, we could just drop an altitude here, and this is a right angle triangle, and we know that this is delta y, this is delta x, and so m, which is our slope, equals, as one should know, delta y over delta x, which is of course just y2 minus y1 over x2 minus x1. And if you were to go through this, you would find that the slope is indeed 1, right? Because you'd have 6 minus 3, which is just 3, and you would have 4 minus 1, which is 3, and 3 divided by 3 is just 1, so the slope is 1, and the slope is going to be 1 no matter where you put your points, right? You could calculate the slope, the change here, the rate of change there. You could calculate the rate of change here. It doesn't matter, it's always going to be 1. Well, what if we have, let's just take that definition and just remember that and keep it in our minds. And now let's just think of something a little bit different, a little bit more strange. And this is sort of what I played with when I first taught myself calculus. This is sort of the idea that I was playing with, and I had a bit of guidance and a bit of lead as well in understanding these thoughts. But in my notebooks, I would say, my old school notebooks, I would say, okay, well, we know the slope of the gradient of a straight line, right? It's very simple, and you can extend that table of values if you would like, and you're going to find that the slope is 1 no matter what. But what if we have a curve? And I'm just going to draw an arbitrary curve. It's no real definition here. And so what if we have a point here and a point here, right? And we make a straight line, right? What is the rate of change here? Or to put it in another way, notice that if we have 2 points and we join them, maybe this is the best approach. Notice if we have 2 points and we join them like this, right? Any 2 points and we join them. I'm just using different colors to denote the fact, so highlight it. And say we have a point here, it's a green line. And I'll make one more line, something a bit more steep, say here and here, right? You have a secant line like that. Well, notice that if we choose 2 points and join them, this produces a straight line, right? It's very clear. And for different pairs of points, we're going to get different lines, right? That's just a very clear, simple deduction from this image. And I suppose the key concept, though, in deepening that, is that we're getting very different gradients. All of these lines are very different, right? And their gradient is very different. And so, in I suppose, thus or hence, that joining different pairs of points on a curve produces lines with very different gradients. And in thinking about that more deeply, let's think of a more formally defined curve. What's common, I think, I see this a lot in different proofs or explanations of differentiation from first principles, and this is the curve I used as well. I think was the curve y equals x squared. It's a very simple curve, obviously, and it's a very good one to experiment with when you're thinking about differentiation from first principles for a number of reasons. Namely because the correlation from x and y points is very simply just square the x value, right? And that becomes handy. So let's just suppose that we look at now y equals x squared. This is just half of it, right, in the first quadrant. Well, as we did with the straight line, let's just create a table of values, and I mean, one should probably already be able to predict what's happening here. F of x, well, actually I'll just put y in this case, okay, and so we've got these points. I'm not going to go too deep into this because this should be quite obvious, but or you should be able to follow this quickly. But so we have x squared, right? So we plug in -2 into our equation here for this curve, and what's this? -2 squared, so it's 4. Likewise, -1 squared is 1. We've got naught, right? That's just naught, 0. 1 squared, 2 squared. Notice, now this is the key. Notice that between the points x coordinates -2, -1, y is decreasing by 3. Now notice that between the x coordinates -1 and 0, it's decreasing by 1. But now suddenly between 0 and positive, on the positive x-axis, 0 and 1, it's increasing by 1. Now it's increasing by 4, or by 3, sorry. And notice, if we were to extend this, say x is 3, well 3 squared is 9, it's now increasing by 5. And what if x is 4? Well, if x were to be 4, I don't know, I'm just plotting an arbitrary point for the sake of definition to understand what's going on here, the correlation between the table and the curve. X is 4, and so it would be up here like this. Well, x is 4, 4 squared is 16. This is increasing now by 7. And you're going to see that all the way along. You can plug any x value here and expand on this. I'm not going to spend much more time on this. But you'll see, so this point here is going to be 16, let's just say, right? But the key realization is that this is not constant, this increase. Rather, just put it this way, the rate of change is in no way, in no shape, no way, no way constant. It's actually all over the place. It's irregular. It's the opposite of constant in a sense, and so as x increases, we're seeing that, well, y is increasing by 1 here, and then y is increasing by 3, and y is increasing by 5. So how do you calculate this rate of change, right? And this is actually a fun thing to do, is to mark this down in your notebook and just think about it. Like, how would one arrive at trying to calculate this rate of change? And Leibniz and Newton were quite brilliant, in fact, at thinking about this. And if you ever get a chance to work through some of Newton, I mean, Newton's my favorite, and working through his Principia at the moment, actually, for fun. But if you get to look, it's quite nice, and you know, to sit here and think, okay, well, how do we approach calculating that value, that rate of change at any point on a curve? Okay, so this is I suppose the meat of the video now, is that we can explain how to calculate the rate of change at any point on the curve y equals f of x. And this is defined to be the gradient of the tangent drawn at that point. So let's just pick an arbitrary point B. The gradient is going to be the tangent at that point B, something like that. Maybe I highlight it in a different color, so just show that it's a gradient, right? It's just kissing at the point B. Now the gradient line is just a straight line, right? So the slope is going to be, right? It's just straight. So at that tangent point, we could calculate the gradient at B. To put it maybe a little bit more formally, that the rate of change at point B is defined to be the gradient of the tangent at B. Now, why is that the case? Well, let's just think a little bit deeper. We can keep this point B, and let's say we've got a point here. We'll call that q sub 1. Say we've got a point here. We'll call that q sub 2. And say that we've got a point here, q sub 3. And we could even make a point q sub 4 if we really wanted to. So why not? Let's do that. Q sub 4 could do what we want. And now we've got a line. It's going to draw a secant line between all of these points B, q sub 1, B, q sub 2, B, q sub 3. And this is going to be hard to magnify in, but then we've got B, q sub 4, right, in orange. It's a little bit close for illustrative purposes, but nevertheless, it might serve the point brilliantly. If the gradient of a curve, and let's keep it general, y equals f of x at any given point, or at a given point, is defined to be the gradient of the tangent at that point, we can use this definition to calculate the gradient at any particular point. Okay, and to consider the graph then that we've got here in front of us. We've got this fixed point B on a curve, and the curve happens to be y equals x squared. And here we have a sequence of points, q sub 1, q sub 2, q sub 3, and q sub 4. And notice that each point, as we work our way from q sub 1 to q sub 4 is getting closer and closer and closer to B, right? Well, why is that relevant? Well, we see that the lines from B to each of these points Q, it's getting nearer and nearer. It's becoming more compressed, compact. It's getting closer and shorter. And it's in more technically, more formally, it's becoming a tangent at B as the Q's near B. The secant line is becoming a tangent line. Okay, and this is the essence of differentiation when we talk of a gradient function. And you can see that it's actually a really clear step between understanding the slope of a straight line, like we did at the outset, to saying, oh, now we have a curve and it's the gradient is all over the place. How are we to calculate that curve, right? The gradient's all over, and then, well, if we drop an altitude down here and here, we start making this connection, and we get a secant line like this, and it's getting closer and closer. It's becoming closer to a tangent, and of course the tangent is just a straight line at a point. And so therefore there's a real conceptual lucidity, isn't there? A coherence in the concept, in the evolution of the idea here. And this is what I mean by calculus is really simple if you just think about it from the point of first principles. And that personally I tend to try to think about things from first principles wherever possible, even though now I spend most of my time studying physics, and on the long road to a PhD I still get to work a lot in calculus. I learn new concepts in calculus, and always I'm trying to drill to first principles, because when you understand concepts from first principles, you can easily navigate any problems that you are confronted with, because you have such a deep logical understanding of the tools at your disposal. And I'm going to stop this video here, and because it is getting on in time, and in the next video, we can call it part 2, I'm going to expand on where we've left off here, and arrive at more formal thinking and conclusion of this series on differentiation from first principles.